Hi guys, so we are looking at section 2.2 today. This section is going to be over verifying trigonometries, as you can see. So talk about how we can verify these trigonometric identities. And then in the next section, we will actually talk about how to solve trigonometric equations. So basically the key in both of these sections, 2.2 and 2.3, is going to be about how good we are at using fundamental identities. And then of course, bringing in some rules of algebra also to help us rewrite these trigonometric expressions. So some terminology you should be familiar with. When we are talking about a conditional equation, you should remember that a conditional equation will be true for some values of the domain of the variable, but not for all. Okay, so you can look at the example here of sine of x equals 0. We know sine of x is only going to be true where your x values are either going to be 0 or multiples of pi, right? So you can have, if basically when they're saying x equals n times pi, if n is 0, your x value is going to be 0. If n is 1, your x value is going to be pi. If n is 2, x value is going to be 2 pi, right? So if you think about, just imagine a unit circle, then you know right here at the starting point, my sine function is going to be 0. Then right here at 180 degrees or at pi, your sine is again going to be 0. And then when you come back a full circle at 2 pi, it's a 0. 3 pi, it's a 0. 4 pi, it's a 0, right? So they're basically just multiples of pi. And then, of course, you can go in the counterclockwise direction and get the same result for negative pi, negative 2 pi, negative 3 pi, negative 4 pi. So that's kind of what they're talking about here. So we know that your x value can be anything because you're talking about an angle here, but sine of x is only 0 at these given values. So that's why sine of x equals 0 is a conditional equation. And they're talking about, when you are finding the values of a variable, that basically means you are solving the equation, okay? Now, the other type of equations that we had talked about was an identity. So an identity basically means that your equation is going to be true for all values of x, right? So it's going to be true for all real numbers of x. And when that happens, you say it's an identity. So you can see this one actually here is your Pythagorean identity, sine square of x plus cosine square of x equals 1. And they've just moved the cosine square to the other side. So they are saying, although there are similarities, verifying a trigonometric equation is an identity is quite different from when you are solving an equation. So, if you're trying to just verify it's an identity, it's not going to be the same kind of thing when you are solving an equation. And like I said, we'll be looking at that in the next section. So you don't really have a set of rules, or as they're saying, a well-defined set of rules when it comes to verifying your trig identities. But these are some really good guidelines here which will help you out. And the idea is the more you practice, the better you will get at it. So as you can see the guidelines here, the first one is talking about start by working on one side of the equation at a time, and it is actually always better to start with the complicated side first. So whichever seems to be the more complicated side, you want to start there first. They are talking about look for opportunities where you can factor an expression, add your fractions, maybe square a binomial, or basically create a monomial denominator. So if you have two terms or a binomial expression in your denominator, maybe you want to see if by using any of the identities, you can create that into a one term or a monomial denominator. Again, guideline 3 is talking about look for opportunities where you can use the fundamental identities. So this will help you basically simplify the expression. Sometimes it may be easier to convert your functions into sine and cosine functions because again, they pair well, you have good identities to work with them. Same thing if you can pair secants with tangents, and of course, cosecants with cotangents. So sometimes those techniques might help you simplify your expression and therefore verify the identities. They are saying when none of these above three preceding guidelines, if they don't work, maybe you can try converting all your terms into sines and cosines and see if something will help you after that. Now, this last one, I really like that. They're talking about always try something. So at least try to break down your problem, see what you can do. Because even making an attempt does not lead you anywhere, you still end up at a dead end. You may actually still learn about, hey, how can I go about simplifying this expression, or verifying my identities. So try something. Don't just give up because you're not sure what you need to do next. It may take you a couple tries, but like I said, the more you practice, the better you will get at it. Okay. um okay, so this last paragraph here is talking about, again, verifying your trig identities is a useful process. Basically, when you're trying to convert a trigonometric expression into a form where it may be more useful to maybe bring one of your algebra concepts in. Excuse me. So if you are able to convert it into an expression where we can then use algebra to solve it, then that might be something you want to look at. They're saying when you're verifying an identity, do not assume. So you cannot assume that the two sides of the equation are equal. So this is very crucial because, the idea is you are trying to verify that they are equal. We don't know that they are equal. So that means you cannot use operations such as adding the same quantity to each side, or maybe trying to do cross multiplication to show that the two sides will be equal to each other. So just keep in mind that you cannot assume that the two sides are equal when you're trying to verify an identity, okay? So let's go about and take a look at how we can do these sort of problems. So your first example here has secant squared theta minus 1, the whole thing divided by secant square of theta, and we have to show that it's going to equal sine square of theta. So remember, they're asking us to verify this, which we don't know if the two sides are equal to each other or not. So the first thing we're actually starting out with is using the Pythagorean identity right here on the numerator. So you've got secant squared theta minus 1. By using the Pythagorean identity, it actually equals tan squared of theta. So that's where we're bringing in the Pythagorean identity. And then the denominator, we're actually keeping it the same. Okay? Then the next thing we're doing, we're keeping this tangent square of theta as it is. This is coming from, again, our numerator. But now we are using the reciprocal identity, which is 1 over secant square of theta is equal to cosine square of theta. So that's where this cosine square of theta is coming in. Then using our quotient identity, we are rewriting tangent square of theta as sine squared theta over cosine squared. Since I have one cosine square in the denominator and one cosine square of theta in the numerator, they both cancel each other out, leaving us behind with sine squared theta. So you can see we have proven that my left-hand side equals the right-hand side, and this is how you can go about verifying your trig identities, okay? Now, one interesting fact here, when we say identity, remember we said that for all values of x in the domain, or in this case theta, your function should be true. But you know what happens in this example here is that when theta is equal to pi halves, pi over 2, your secant square of theta function is actually going to be undefined because that's, of course, your 90-degree angle, right? And that's where your secant function is undefined because that's where you end up dividing by 0. So even though we are proving this as an identity, there is one value of theta where your function is going to be undefined. So just kind of something interesting to keep in mind. Okay, and then just another note here, we're saying notice that you verify the identity by starting with the left side of the equation, which was the more complicated side, and using fundamental trigonometric identities to simplify it, we came up with the right-hand side. So we're going to use that same kind of technique in our example here, example 1. So we are given sine square of theta plus cosine square of theta, the entire thing divided by cosine squared theta, secant squared theta, and we have to show that this will equal 1. So let's take a look at how we can go about verifying this. So let's come over here. All right, so I've got my problem written down. So the first thing I'm actually going to use is the Pythagorean identity, which is sine squared of theta plus cosine squared of theta equals 1. So this is our numerator. So that means I can rewrite my numerator as 1 using this Pythagorean identity, keeping my denominator the same for now. Okay, and basically we don't know if the left-hand side equals the right-hand side. So let's go ahead and put a question mark on our equal to, because we don't know if the two sides are equal or not. Okay, now what I'm going to do is, since I am multiplying the cosine square of theta with secant square of theta, I'm actually going to separate these into two fractions like this. So I'm basically just splitting that denominator apart. And again, we're trying to verify if this will equal 1. So if you think about this, your 1 over secant square of theta is the reciprocal identity for cosine square of theta, right? So I'm actually going to rewrite my second fraction. I'm going to keep the first one as it is. So leave that as 1 over cosine squared of theta. And then rewrite my second one by using this reciprocal identity here, and rewrite this guy as cosine square of theta. And again, we're trying to verify if this is equal to 1. So same thing here. I've got a cosine square of theta on the numerator. I've got a cosine square of theta in the denominator, so I can cancel both of them out. And as you can see, once they cancel out, I end up getting 1 equals 1. So that's obviously we got the same result, which means I can say this has been verified and our left-hand side is indeed equal to our right-hand side. So as you can see, each problem is going to have a different approach on how you go about solving it. So this was our problem 1 here. All right, let's go back to our notes. So if you actually come back to this example 1 right here, they are showing us a little bit of a different approach on how we can solve this problem using a little bit of a different technique. So that's going to be at the bottom of this page. So basically here what they did was they took the denominator, and using the denominator, they separated the numerator. So you've got secant square of theta over secant square of theta. And then using the minus sign, we're separating our second fraction. So that's 1 over secant square of theta. Secant square theta cancel each other out, giving us 1 from here. Again, you're using the reciprocal identity for 1 over secant square theta, which is what gives you the cosine squared of theta. And then again, using your Pythagorean identity, 1 minus cosine square is equal to sine squared theta. So that was another way that you could have verified this example 1 identity in here. So as you can see, even for that same problem, you have different ways of verifying the identity. So each one of you will have a different way of solving this, which is fine. Just make sure you're using the right identity and using the correct rules of algebra to verify these. All right, guys, let's go on to example 2 here. Again, they're asking us to verify the identity. We are given 2 secant squared alpha, and that is equal to 1 over 1 minus sine alpha plus 1 over 1 plus sine of alpha. So what we're actually going to do here is start on the right-hand side, because obviously you can see that's the more complicated side. And you are actually going to find the common denominator, which means you multiply both the denominators together and then multiply your numerators with the other denominator, so the other side. So in this case, we end up multiplying our first fraction here by 1 plus sine of alpha, and you end up multiplying the second fraction by 1 minus sine of alpha. So that's where you get this expression here. You've got 1 plus sine of alpha added with 1 minus sine of alpha, and then of course your denominator will be both the denominators from the original right-hand side, okay? Now on the numerator, you've got a positive sine alpha and you have a negative sine alpha. So they actually end up canceling each other out, and then you're left with 1 plus 1, which is where this 2 comes from. And then you're basically going to multiply or FOIL your denominator, and which is where this 1 minus sine squared alpha comes from. So again, 1 minus sine squared alpha using the Pythagorean identity will become cosine square of alpha. So you are now left with 2 times 1 over cosine square of alpha. And remember, 1 over cosine square of alpha is the same thing as secant squared of alpha. So that is where 2 times secant square of alpha is coming from. This 2 is basically the same 2 that you have from the numerator, and then 1 over cosine square alpha ends up becoming secant square alpha. And of course, that now matches the left-hand side of the identity, and we have again verified that these two identities are, the left-hand side is equal to the right-hand side. Okay, so let's take a look at our example, which is very similar to example 2. We are given 2 times cosecant squared beta equals 1 divided by 1 minus cosine beta plus 1 divided by 1 plus cosine beta. So it's actually going to be very similar to what we did here in example 2. So let's go ahead and take a look at this problem here. All right, so I've already got this written down. So remember, we're going to start on the right-hand side since that's the more complicated side. So we need to find a common denominator, which means multiply this fraction by 1 plus cosine beta, numerator and denominator. And then multiply this fraction by 1 minus cosine beta, again, both numerator and denominator. So that will end up giving us 1 times 1 plus cosine beta, of course, gives us this. Your denominator will be 1 plus cosine beta, 1 minus cosine beta. Same thing on that right-hand side, 1 times 1 minus cosine beta will give you this, and then our denominator. So this is how we find our common denominator. So since it is a common denominator, I'm actually going to bring them together. And then add your numerator, so that's 1 plus cosine beta plus 1 minus cosine beta. So again, you will notice we have a positive cosine beta and a negative cosine beta, so they will end up canceling each other out. You're left with 1 plus 1, which gives us 2. FOIL your denominator, or if you remember, this is basically of the form a plus b multiplied with a minus b, which ends up giving you a square minus b square. So you can actually just use that idea of a square minus b square to help you out. And that will end up giving us a square would be the 1 square. So that's 1 times 1, which is 1. Minus b square will be cosine beta. So that's going to be cosine beta squared, or cosine squared, cosine squared beta. So you can do it this way, okay? And then this is where we're going to bring in our Pythagorean identity again. So remember, sine square beta plus cosine square beta equals 1. If I move my cosine square beta to the other side, you end up getting 1 minus cosine square beta. So you can use this identity to rewrite your denominator. Because remember how we had talked about it's always better to try and get a monomial denominator. So that's basically what we're doing. So replace your 1 minus cosine square beta with sine square beta. And then we are going to use the reciprocal identity. So 1 over sine square beta as a reciprocal is going to be cosecant square beta, right? So that will give you 2 times. And if you want, you can kind of separate that denominator like this. And then that will become 2 times cosecant square beta, which is what we were trying to prove. 2 times cosecant square beta, which was our left-hand side in this case. And so now we can say this has been verified. And again, remember, we're not entirely sure that these guys are equal, so you can always put these little question marks till you are 100% certain that you have verified your identity. Okay, so on the last one, you don't need to put the question mark because this is where we're showing they are in fact equal to each other. Okay, so a little bit of a lengthy process. Now, of course, you don't have to write as many steps as I wrote in this one, but I just wanted you to see how that transformation happens and how you can prove that this identity in fact is equal, right? All right, so that's our example 2. Okay, let's look at example 3 here. So they're talking about verifying the identity, and then in parentheses, you've got tangent squared of x plus 1 being multiplied with the quantity cosine squared of x minus 1, and we have to show that this product will equal negative tangent squared of x. Okay, so the first thing we are actually doing is using the Pythagorean identity and rewriting tangent squared of x plus 1 as secant squared of x. And with the second one, let me show you how they're getting the negative sign of x squared here. So your Pythagorean identity for that is sine squared x plus cosine squared of x equals 1. So the first thing we're going to do is subtract the 1 on both sides. So this guy will cancel out. And then we are also going to take our sine squared of x and subtract that also on both sides. So that will cancel out here, leaving you behind on the left-hand side. We have cosine squared of x, and then don't forget this minus 1. And then on the right-hand side, you have negative sine squared of x. So basically, your cosine squared of x minus 1 becomes the negative sine squared of x. So that's how they're doing that little calculation. So now your negative sine squared of x is here on the numerator. And then they are using, again, the reciprocal identity, where they are taking secant squared of x and rewriting it as 1 over cosine squared of x. And that's where this denominator of cosine squared of x is coming from, by using this reciprocal identity. And then remember, sine of x over cosine of x gives us tangent of x. So now you're just making these squares. And so that's why sine squared of x over cosine squared of x becomes tangent squared of x. And then that negative sign from this original sine function here, that negative sine squared of x, that negative sign will basically stay till you get to the end. And you can see we have verified that our left-hand side is again equal to our right-hand side, and we get negative tangent squared of x. So we are getting the original identity checked out. Now your textbook is also showing you graphical solution. So you will notice they've taken the left-hand side of the equation and put that as one function, and they've taken the right-hand side of the identity and put that as the second function. And they're basically showing you that when you graph each side separately, they come out to be the same graph. And since they are the same graph, or as they're saying, the graphs are coinciding, we know that this identity is going to be true. So that's kind of how the graphical method works. But of course, we are not using graphing calculators or any kind of graphing technology, so you will not have to do the graphing part. Okay, so just the verification part by using the identities and by using algebra. So let's take a look at how we can simplify this example 3, which is given to us. So we are given the quantity secant squared of x minus 1 is being multiplied with the quantity sine squared of x minus 1. And we have to show that this product will equal negative sine square of x. Okay, so let's take a look at this example here. Okay, so the fundamental identities we will be using here is 1 plus tangent squared of x is equal to secant squared of x. So if I subtract 1, you end up getting tangent squared of x equals secant squared of x minus 1. So that's what we are going to use to make this little substitution happen. So instead of writing it as secant squared of x minus 1, I'm going to replace that with tangent squared of x. Okay, and then for our sine square of x minus 1, again, that's coming from the Pythagorean identity again of sine square of x plus cosine square of x equals 1. So if I subtract the 1 and bring it here with the sine function, and then I take my cosine function and move it to the other side, these guys will cancel out here, and then on the left hand side you are left with sine square x minus 1. On the right hand side you are left with minus cosine square of x. So that's where this substitution will happen. So instead of sine square of x minus 1, you're going to replace that with negative cosine square of x. And again, we are trying to show if it can equal negative sine square of x. So we don't know if it will, right? Okay. So now we're going to have to use the quotient identity to rewrite our tangent squared of x. So remember, tangent square of x can be written as sine squared x over cosine squared of x. So now we're going to rewrite this guy as sine squared of x over cosine squared of x, and I'm multiplying this with negative cosine square of x, and we need to show if it will equal negative sine square of x, right? Okay, so as you can see, I have a cosine square of x on the denominator, a cosine square of x on the numerator. We still have this negative sign left over, so bring that guy down. And then, of course, you have the sine square of x left over. And you can see, again, we are able to verify that the left-hand side is equal to the right-hand side. So this is our verified answer. Okay, so there you go. Not too bad. You just had to use, I guess, 3 different identities here to help you simplify this. But once you do that, it doesn't seem that hard to go about, solving these problems. So that was our problem number 3. Okay, let's look at example 4 here now. So example 4 is basically going to be the approach where we try to convert our functions into sine and cosine functions and then see how that will help us verify these identities. So looking at example 4, part A is given to us as tangent x times cosecant x is equal to secant x. So if you look at the solution part, we are rewriting tangent x as sine over cosine. We are rewriting cosecant x as 1 over sine. So I have a sine on the top, sine on the bottom. They end up canceling each other out. You are left with 1 over cosine of x. And 1 over cosine of x is, of course, the same thing as secant x. And you were able to verify part A. In that same way, looking at part B, you are given tangent of x plus cotangent of x is equal to secant x times cosecant x. So let's take a look at part B over here. Again, you are rewriting tangent x as sine x over cosine x. You are rewriting cotangent x as, of course, the reciprocal. So that's the cosine of x over sine of x. Then, just like we did previously in example 2, go ahead and multiply both the denominators with both the fractions. So the left-hand side, you multiply that with sine of x. The right-hand side, you multiply with cosine of x, which is where sine square of x plus cosine square of x is coming from. And then, of course, the common denominator of cosine x times sine x. Now, guys, on the numerator, where you have sine squared of x plus cosine squared of x, that's your Pythagorean identity, and you know that equals 1, so that's where this 1 is coming from. And then keeping our two common denominators. Now, since you are multiplying these guys, we're separating this as 1 over cosine x and 1 over sine x, and then using your reciprocal identities, 1 over cosine x becomes secant x, 1 over sine x becomes cosecant x, and again, you can see we were able to verify the identity in part B. So that's kind of how part B works out to be, okay? And again, you'll see we are also dealing with similar examples to, or similar problem to what you saw in example 4. So let's take a look at part A over here. You are given cotangent x multiplied with secant x, and we have to show that it will equal cosecant of x. So let's take a look at this guy. Okay, so cotangent x, secant x. So we can actually use, for the cotangent x, the quotient identity again, which is cosine of x over sine of x. So let's rewrite this guy. Cosine of x over sine of x. And then for the secant function, of course, you can use the reciprocal identity, because remember, you're converting these into sine and cosine functions to try and verify these identities. So secant will become 1 over cosine of x. So let's rewrite this guy. And remember, you're multiplying these as 1 over cosine of x. And of course, your cosine on the numerator, cosine on the denominator will cancel each other out. And again, we're not sure if these guys are equal to each other. So let's put that question mark. Okay, so on the left-hand side, once we cancel out our cosine functions, you are left with 1 over sine of x. And of course, 1 over sine of x is your reciprocal function, which gives you cosecant x equals cosecant of x. So again, guys, we have verified this identity. Okay? So that's again using the reciprocal function. That was the identity that we used. Okay, let's look at part B. So part B, we were given cosecant of x minus sine of x, and we have to show it's equal to cosine of x times cotangent of x. Okay, so again, we're going to start by using the reciprocal identity for the cosecant function, which is of course 1 over sine of x. So let's rewrite this guy. 1 over sine of x. Since this guy is already a sine function, you can leave it as it is. And of course, our goal is to show that it can equal the right-hand side. So let's leave that right-hand side as it is. Now, this sine of x, you can actually write it as sine of x over 1. And then to find your common denominator, you basically end up multiplying this function by sine of x so that we can have a common denominator. So this guy will stay the same. This guy will become sine of x times sine of x. So that's sine squared of x. and then 1 times sine of x is sine of x. Now, if you're wondering, why did I use sine of x to multiply my second fraction with? That's because my first fraction here has a denominator of sine of x. So it's actually coming from this denominator here that I am multiplying the second fraction by sine of x also. And again, we're trying to show if it will equal the right-hand side or not. So since both my denominators are now the same, I can write this over a common denominator. And you can have 1 minus sine squared of x, right? Just bring it all together. And then this is where your Pythagorean identity kicks into place. So remember, sine squared of x plus cosine squared of x equals 1. If you move the sine squared function to the other side, you end up getting 1 minus sine squared of x, right? So now I am going to replace my numerator. Denominator will stay the same. So the numerator will get replaced with cosine squared of x. And again, we're trying to show it can equal the right-hand side. All right, so now how do we get to that cosine x times cotangent x? So this is really simple at this point. You have cosine squared, which means you have cosine times cosine on the top. So go ahead and separate it out. Okay, and then you've got the sine of x on the bottom. But you know what you can do is just put that sine of x under the second cosine of x like this. And you can see why we're doing that. Because we need to have a cosine of x on the first part and a cotangent of x on the second part. So the first part, cosine of x, will stay as it is. And then using our quotient identity again, you should remember cosine of x over sine of x is equal to cotangent of x. So the second part will now become cotangent of x, and we have verified that our left-hand side is equal to our right-hand side. There you go. And again, you know, I may be using a lot more steps than what you want to. Again, you don't have to break it down as much as I am, but this was again just to show you step by step how you can show the verification process and show that the left-hand side will in fact equal the right-hand side. And again, you can see we have verified that this identity is true, and you are done here with part 4b. Yep, there you go. Alrighty. So rationalizing the denominator, you know, of course, we talked about that quite a bit in college algebra, but we also talked about it in chapter 1 when we were doing the right triangle trigonometry, because, you know, the idea is we never leave a radical in the bottom of our denominator. So we always multiply, like if you had 2 over square root of 3, you would multiply your numerator and denominator by square root of 3 to get rid of that radical on the bottom. So in that same way, you know, sometimes we have to multiply the denominator by a conjugate. Now, when you are talking about conjugates, basically the idea is if one expression is a plus b, its conjugate is going to be a minus b, or vice versa, right? If the original is a minus b, then its conjugate is going to be a plus b. So that's what they're talking about. So sometimes for rationalizing the denominator, you actually need to multiply by the conjugate to simplify your denominator. So that's kind of what they're talking about here. So we are given this 1 over 1 minus cosine of x, and you are seeing here that we are actually multiplying both the numerator and denominator by its conjugate. So since this guy is 1 minus, the conjugate of course will have 1 plus cosine of x in it. So multiply your numerator, you get 1 plus cosine of x. Foil your denominator, and it's going to give you 1 minus cosine square of x. So again, you're using the Pythagorean identity to rewrite that denominator. 1 minus cosine squared of x as sine squared of x. And then again, guys, for this last part, 1 over sine squared of x using the reciprocal identity is going to be cosecant squared. So that's actually where this cosecant squared of x is coming from. And then this numerator of 1 plus cosine of x, it stays right here with it. So that's basically how they are simplifying your 1 over 1 minus cosine of x. So a lot of times, when they are asking us to simplify an expression, just getting rid of the fractions can be considered as simplifying your expression. So this is a pretty neat trick that we are actually going to be using in this example number 5 here. So you can see we are given secant of x plus tangent of x equals cosine of x over 1 minus sine of x. So this is definitely where you can see that we will need to use the conjugate process here, or basically, as we call it, rationalizing the denominator trick to help us out here. So look at the solution for this guy. So we're taking that right-hand side, cosine of over 1 minus sine of x, multiplied by the conjugate of the denominator, which is the 1 plus sine of x, both the numerator and denominator. So in the numerator, you're actually distributing this cosine of x inside the parentheses, and then you're going to FOIL the denominator. So that's where you're getting cosine of x plus cosine of x sine x on the numerator, 1 minus sine square of x on the denominator. Keeping the numerator the same, you're using the Pythagorean identity to rewrite that denominator, 1 minus sine squared of x as cosine squared of x. And then using this plus sign here, we are separating our fractions. So you've got cosine of x over cosine squared. You've got cosine x sine x over cosine squared. So one of these cosines will actually cancel out on both sides, and you will be left with 1 over cosine of x using the reciprocal identity. That will become secant of x, and sine over cosine of x will of course become tangent of x, and you can see that's what we had on the left hand side. So by using this concept of rationalizing the denominator, we were able to verify this identity for number 5. Okay, and again, guys, you will see they're using the graphical solution again. So the left hand side is one function, the right hand side is one function, and once you can show that your graphs coincide, you can say that the identity is true. And again, remember, we're not using the graphical solutions for our examples. So let's see how we can go about doing problem number 5 here. We are given cosecant of x plus cotangent of x is equal to sine of x over 1 minus cosine of x. So let's say if we can prove this identity here. So remember, you will start by taking the right hand side, which again is the more complicated side. So we'll multiply both the numerator and denominator by the conjugate of the denominator. So this guy is 1 minus cosine of x. You multiply by 1 plus cosine of x, both numerator and denominator. Okay. And again, we don't know if these two sides are equal. So remember, you will need to distribute this sine of x inside the parentheses, and then you can either FOIL or use the idea of a plus b multiplied with a minus b is going to be a square minus b square. So the numerator will become sine of x times 1 is sine of x, plus sine of x times cosine of x will of course give us sine x cosine x. And then our denominator will be a square minus b square. So your a is 1. So 1 squared is 1 minus cosine times cosine will of course give us cosine squared of x. Okay. For the denominator, I am going to use the Pythagorean identity. So if you take the cosine to the other side, you end up getting sine squared of x is equal to 1 minus cosine squared of x. So using this Pythagorean identity, you can rewrite your denominator as sine squared of x. And then for now, keep the numerator as it is. Okay, with me so far? So now this is where, using this plus sign, we are going to separate our fraction. So you're going to have sine of x by itself divided by sine squared of x, right? And then, like I said, using that plus sign, now separate the other part. So that's going to be sine of x times cosine of x, and again, same denominator, sine squared of x, okay? So like you saw in the example before this one sine of x will cancel out one sine of x from the denominator. This sine of x will cancel out one sine of x from the denominator. So since my numerator canceled out, you can put a 1 in its place. And out of the sine squared, only 1 canceled out, which means one sine of x is still remaining. On my second fraction, the sine of x canceled out, but we still have that cosine of x left behind. So cosine of x, and then again, denominator sine squared, one of the sine cancels out, one of the sine of x is still left behind, okay? And then here, you can use the reciprocal identity. So 1 over sine of x is of course going to be your cosecant of x, and cosine of x over sine of x of course gives you cotangent of x. So using these, we can make our substitution. So 1 over sine x becomes cosecant of x. Cosine of x over sine of x will become cotangent of x. And let's see, yep, cosine plus cotangent, cosine plus cotangent. And again, these guys up until the last step are going to be question marks. And here we have just verified our identity, cosine of x plus cotangent of x. There you go. Okay, so that's your example 5. So out of all the examples we have done so far, all 5 of them, basically you were taking one side, simplifying it by using the fundamental identities or rules of algebra to show that it would equal the other side, right? So you were working either on the left-hand side or right-hand side and trying to show it will equal the other side. But sometimes you may actually have complicated functions on both sides of your equation. And in that case, it may actually make more sense to solve each of the side separately and show that they will end up equaling the same expression. So what's going to happen here in example 6 is we're going to solve the left-hand side, we're going to solve the right-hand side, and try and show that they are in fact going to be the same expression, and that's how you're going to verify the identity. So let's take a look at this guy here. You've got cotangent squared theta over 1 plus cosecant theta, and we have to show that it's equal to 1 minus sine of theta, the whole thing divided by sine of theta. So let's start on the left-hand side. You've got cotangent squared theta. So this is actually using the Pythagorean identity to rewrite cotangent squared theta as cosecant squared theta minus 1. You're leaving the denominator the same. And then since cosecant squared theta minus 1 is in the form of a squared minus b squared, you can factor it into a plus b, a minus b, which is how they're getting this numerator here being factored. So that's cosecant theta minus 1 multiplied with cosecant theta plus 1, and then leaving the denominator as it is. Now, since cosecant theta plus 1, both of these are positive values, you can actually rewrite it as 1 plus cosecant theta. So these values are actually the same, and that's why you're able to cancel them out, which leaves you behind with just that cosecant theta minus 1, okay? So remember, this was us just simplifying the left-hand side. Now we need to simplify the right-hand side to show if this is an identity or not. So we are given 1 minus sine theta divided by sine of theta. So again, using this minus sign, we're going to separate them into two fractions. You're going to take 1 divided by sine theta, and you're going to take sine theta divided by sine theta. So 1 over sine of theta, of course, becomes cosecant theta, and then sine theta divided by sine theta ends up becoming 1. So you can see, since we got the same result on both sides, when we simplified it, you can say that they are in fact equal to each other, which means we have an identity for number 6. So a little bit of a different approach, right? And that's the exact same thing we are going to try and do with our problem number 6. So we are given tangent squared of theta divided by 1 plus secant theta, and that's equal to 1 minus cosine theta over cosine of theta. So let's take a look at this problem 6 here. Alrighty, so I'm going to start with the left-hand side, and again, we don't know if they are equal to one another. So let's start by rewriting that tangent squared of theta. So it's tangent squared theta plus 1 is equal to secant squared of theta. And then if you just get tangent by itself, move that 1 to the other side, sorry. You end up getting tangent squared theta is equal to secant squared theta minus 1. So I'm actually going to rewrite my numerator as secant squared theta minus 1 and leave the denominator as it is. So your secant squared theta is in that part of a squared minus b squared. So you can factor that into a plus b, a minus b. So by factoring our numerator, you will get secant theta minus 1 multiplied with secant theta plus 1. So that's your a minus b, a plus b, leave your denominator as it is. So keep in mind, secant theta plus 1 is the same thing as 1 plus secant theta, because my 1 is positive, my secant is positive. So just switching the order does not change anything. So secant theta plus 1 will cancel out 1 plus secant theta. They are the exact same expression. And that leaves us behind with just this value from the top, which is secant theta minus 1. Okay? So now you have to show that the right-hand side can also be simplified into secant theta minus 1 if you're going to verify these identities. So let's start with our right-hand side now. You are given 1 minus cosine theta over cosine theta. So I'm going to separate these into two fractions. So you can rewrite this guy as 1 over cosine theta minus, then the second side, cosine theta over cosine theta. So 1 over cosine theta using the reciprocal identity will become secant theta. So let's rewrite this first fraction as secant theta, and then cosine theta cancel each other out, giving you 1 as the answer. And we are able to show that both sides, when simplified, will in fact become secant theta minus 1 equals secant theta minus 1. So this is how we can verify number 6. Okay, so this is where, like I said, you do each side individually and then try and show that the two expressions will in fact be equal. So that was example number 6. Okay, so that brings us to the last part of this section where we are talking about where you can show that the powers of trigonometric functions can be rewritten as more complicated sums of products of these trigonometric functions. So this is actually a procedure which is pretty commonly used in calculus. So if you ever end up taking a calculus course, this will definitely come in handy. So looking at our part A for 7 example, we've got tangent to the fourth power of x, and they're asking us to basically verify that it's going to equal tangent squared of x, secant squared of x minus tangent squared of x. So basically, since this is tangent to the fourth power, you can break the fourth power down into 2 times 2. So that's where they've got tangent squared multiplied by tangent squared. They're leaving this first tangent squared as it is, and they're actually using the Pythagorean identity to rewrite tangent squared as secant squared of x minus 1. And then to get that final answer, they're actually just taking this guy and distributing it inside the parentheses. So you get tangent squared multiplied by secant squared of x, which gives you this, and then tangent squared multiplied by 1, which gives you this minus tangent squared of x. And this is how we are able to verify part A for number 7. Now part B is talking about cosecant to the fourth power of x multiplied with cotangent of x, and we have to show that it will equal cosecant squared of x, and then in parentheses cotangent x plus cotangent cubed of x, right? So let's take a look at this part B here. You are taking this cosecant to the fourth power of x, and again rewriting it as cosecant squared of x times cosecant squared of x. So basically, again, taking that fourth power and breaking it down into 2 times 2. This cotangent of x, you're actually letting it stay as it is, okay? So this first cosecant squared of x, you're actually keeping it as it is. This cotangent of x, you are also leaving it as it is to the end. It's this middle cosecant squared that you are rewriting using the Pythagorean identity as 1 plus cotangent squared of x. And then for the very last thing, you're taking this cotangent of x and you are distributing it inside the parentheses. So this cosecant of x stays the same from the front here. And then you're taking 1 times cotangent, which gives you cotangent of x. And then cotangent squared with cotangent gives you the cotangent to the third power of x. So that's how you're actually verifying part B, for example, 7. Okay, so this is actually using, again, your rules of algebra, just to break this down, included with the fundamental identities here. So let's look at our problem 7 here. So part A is actually very similar to part A of example 7. Example 7 had tangent to the fourth power. We have tangent to the third power, and we have to show it's going to equal tangent of x multiplied with secant squared of x minus tangent of x. So let's look at that part A for number 7 first. So tangent to the third power. So for this third power, we're actually going to break it down into whoa, I don't know what I did. Okay. So we're actually going to break down that third power in the first power plus the second power. So let's rewrite this guy. And again, we're trying to prove that these guys are equal to each other. So tangent to the third power, you will write it as tangent times x. Tangent of x, and then tangent squared of x. So you're breaking that third power into the first and the second power, okay? And then we have to verify that it's going to equal this right-hand side. All right, so now I'm going to use our Pythagorean identity again. So if you want to get tangent by itself, move the 1 to the other side, and you get this, okay? So I am going to rewrite this second part, and I'm going to keep my first part of tangent x as it is, and replace my tangent squared of x with secant squared x minus 1, and again, we're trying to verify it's going to look like the right-hand side. And then at this point, we're almost there. All you have to do is take this tangent of x and distribute it inside the parentheses. So you will end up getting tangent of x multiplied with secant squared of x minus tangent of x times 1, which gives you tangent of x. And of course, you can see our left-hand side will match our right-hand side, and this is how we can verify that the two sides will be equal. And I'm just going to put a little ditto over there. Okay, so this is how you're basically showing how the left-hand side will equal to the right-hand side. So again, not too bad. Now, let's take a look at part B. So for part B, we are given sine to the third power of x multiplied with cosine to the fourth power of x, and we have to show this equals cosine to the fourth power of x minus cosine to the sixth power of x, and this whole thing multiplied by sine of x. So that's this part B right over here. Okay, so again, I'm going to start on the left-hand side, and I am actually going to rewrite our sine of x with the third power. Again, I'm going to break this down into sine of x and sine squared of x, and I will keep that cosine to the fourth power as it is for now. Okay, and we have to show that it's going to equal the right-hand side. Now for my sine squared of x, I am going to use our Pythagorean identity. So to get sine squared by itself, we'll go ahead and move our cosine squared to the other side. So leave your, leave your first sine of x the same. Replace your second sine squared of x with this Pythagorean identity. So sine squared of x will be replaced by 1 minus cosine squared of x, and then just bring down that cosine to the fourth power of x. And again, we're trying to verify this. Now, as you will see, we need to leave that sine x as it is from the right-hand side, but we need to actually take this cosine to the fourth power and distribute that inside the parentheses. So I'm going to leave my sine of x as it is, and I'm going to take my cosine to the fourth power multiplied by 1, which will give me cosine to the fourth power of x minus, and then I'm going to multiply the cosine to the fourth power with cosine to the second power, so that's 2 plus 4, which will give us cosine to the sixth power. And basically, you know, at this point you have actually verified it, but if you want to make it look the same, you can take the sine and put it at the end, so you can have your cosine to the fourth power of x minus cosine to the sixth power of x, and then you can put that sine of x at the end, and this will look exactly the same like your right-hand side, and you can say that you have verified this identity. So the left-hand side will match exactly the right-hand side. And there you go. That's all you have to do for this 7B of our problem here. And like I said, that's the end for this section. So look through these examples, look through this problems that I did, and then let me know if you have any questions, okay? All right, guys, I will see you later.